All right, so inevitable happened. This is the final class of this quarter. I am excited and sad both way, but I know that this is exciting. Some of you are graduating, some of you will continue, and I'll see you guys in next year, hopefully in person. But I enjoyed it, and so today we are going to discuss at least first few minutes to share with you my our experience. So first, Renan, who is the TA here, he did amazing job, and he made my work a lot easier. So I'm very thankful for him to be a TA here. And so he will say a few words before I start saying it. So Renan, you have 5 minutes to talk about your experience and what you learned about this class as well as students.
All right. Thank you, Sanjay. Thank you, everyone. It was a very fun experience, even though it was in Zoom this quarter. I really enjoyed teaching the class, and the session at 8 a.m. wasn't on Friday wasn't the the most appropriate time, but I'm glad you guys could come. We could record the sections and share it online. So today, as a farewell, I just wanted to show or share a few things that I've learned in this class throughout this quarter. So I believe when I was thinking of this, I think one of the best things that I've seen this quarter is like the diverse backgrounds and how everything comes together. We've had graduate students, undergrads throughout the campus coming all to work on green infrastructure, and that's really interesting when you think of the brainstorming behind these diverse backgrounds. Um, because whenever you do some brainstorming where people um, bring things from their own areas, you can really improve science. That's how you advance something in science. That's how you create something new. So those different perspectives are very, very important um, for the project that you guys did, as well as for the future. It's important to have these diverse ideas on the table because whenever you have those diverse ideas, you bring new things to the table because it's part of human beings. We stick to the things that we know, and we want to keep doing that. Um, but whenever someone shows you something new because they have a different perspective, one, you learn something new. Two, you take those experiences and you apply to your own expertise. So you can even advance your own expertise by learning something new. And therefore you can create new things for the society and in your career or in this project, for an example. Um, Another thing that I've learned about green infrastructure and throughout this project, because you guys would bring a lot of different articles, different perspectives. Something that I've learned is that this class goes beyond cleaning water and air or green infrastructure in general, goes beyond that. And I say that because there is a lot of implications of green infrastructures on education of people. So I've read one of the papers that some group shared, and it talks about the importance of having green spaces in school and how those green spaces actually um, it helps the kids be more motivated to learn and to go to school, and that's very important, right? Sometimes school can be kind of annoying, but it's everyone needs to learn. Everyone there's a lot of good things in school, so we need to think how do we make these experience more enjoyable for the kids, and the application of these green spaces, which are going to clean air and water, actually have an indirect impact on these kids life. um, there's also a lot of indirect education whenever you have green infrastructure in schools, because the stormwater biofilters, let's say it's they're cleaning water, but at the same time, the teachers can bring those kids to the biofilter and have a class, like an hour class there, where they're going to be talking about these green infrastructures and educating those kids for the future about the importance of having those green infrastructures in place. Because if you don't have those green infrastructures, it's really hard for kids to relate if they don't see it. And therefore, that would improve awareness for future generations to implement more and more green infrastructures. Um, and last but not least, it's the future of green infrastructures. Uh, I've I've seen in all of the projects how much space we still have that we can implement more and more green infrastructure. And that it's also translated into jobs for the future that we are all here. Many of you guys are going to end up in environmental engineering fields or green infrastructure. Know that there is a lot of space and therefore a lot of jobs. And I just wanted to share this picture here that it's part of the project of one of the class, the groups. And in the bottom picture, or the bottom half of the picture, it's an elementary school. And you can see that there's literally no green spaces there. It's somehow like depressing, you know, even though depressing it's kind of like an intense word, but it is somehow depressing to be in that space. You can think how hot it can get, um, the air pollution with dust and stuff. But whenever you look at the upper part of this picture, you can see that it's the city hall, and the city hall is full of green spaces, which is where all the politicians are. So you can see a clear contrast between, you know, the school that all where all the kids are learning or we we hope that they learn there. And the politicians know that like these, it's pleasant to have this green infrastructure. It's good for the environment, and they apply to their place, but they do not really look at the school that it's literally 10 feet away from their workspace. So this is just to show a contrast how much space we still have to improve, and the importance of having those spaces for our kids and for our society. Um, so that was pretty much it. Thank you, everyone. I really learned from you guys, and I really enjoyed teaching and connecting with you. Also know that it's not because it's the end of the term that I'm not reachable anymore. Feel free to, you know, email me or access my website to keep up with the work that we're doing. I'm always happy to contribute and like, you know, exchange experience, and like if you need any feedback on, you know, science, environmental engineering, or beyond that, feel free to reach out to me. It's better.
Thanks, Renan. This is a wonderful. Yeah, we all agree. I particularly heard good thing about you. So I am thankful that you are here. Next year, Renan is graduating with PhD. He could graduate if he want to this year. That's the beauty of his PhD, that he is eligible to get a doctorate degree, but he's staying because he want to learn more. Um, so I'm really excited that Renan will do a lot of different works on this area. He's very much interested in data science of aspect of environmental engineering, something that you guys should also consider, because he enjoy looking at data and seeing how what stories stays. So he was a bestie, I would say, in this for this class. I would miss him next year. Let's see, how if I can find somebody like him. Uh, all right, so I
Thank you,
guess
Sanjay, for the words.
thanks, Renan. If you want to stay, Renan, stay. Otherwise, I'll stay as long as you want. If you want to, there's no.
Yeah, I'll be working, but I want to keep listening to the
Okay.
presentation, so I'll be around. Thank you.
So I am going to say a few words before we have it's all for you, because I know that many of you leave. Okay, let me share the screen. Let's see. Okay, so again, this is final presentations, and I want to have some announcement as part of the recording, because I know that many of you might have these questions. So first thing is check Friday and Saturday for my emails with comments on your projects. One thing I could not do is reading your projects as much I wanted, so I didn't provide any comments. Thankfully, Renan gave you many comments to start improving. So work on it whatever you can until I get my comments. Then I'll give you some extra comments to work on. And again, just because I give you comments or Renan give you comments doesn't mean that we expect you to address many of them, but we may not may have misunderstood your projects, or So make sure to email back if you don't understand some comments. That way we can see whether that's actually valid or not. So it's a back and forth feedback. So you don't feel free to discuss with us. And second, midterm grade, it will be live on Monday. Um, Check from Monday to Friday because you have your solutions. Check just in case any places where you made a mistake. By Friday or next week Saturday, if you give us anything, because I'll not release the grade until Sunday, right? So on Sunday next week, Sunday or Monday, whatever the date is. So by then, any times you have a difficulty about your either homework grades or midterms grade, or so anywhere it's not reflected well, let us know, because once I open it, grade submit the grades, it's a little bit more difficult to provide the changes. But until then, as I said, it's easier for us from our end to change it. And same thing, check homework grade, but in general, nobody lost a lot of points. It's very, homework, you don't lose normally points if you have a given effort. We don't take points for wrong answers or all that. So that's the one I would know. Just things to check is whether you have submitted homework to me and it's not reflected there because other people are grading. So if just in case I miss it, just make sure it's there. I know that some of you send me email, but just check, double check there. And again, suggest any change in grades for midterms or homework by Friday or Saturday next week. By if you do after Sunday, it may be late. So that's all I want to say. So right now, the only due dates is final projects, which is due next Friday. Once you receive the comments, I believe it should not take more than 1 day for you to address any comments, because I normally don't give extensive comment because you have already given effort. And I have seen it. It's not like your projects are bad. Your projects are pretty interesting and very good, many of them. Thanks to Renan. Right now, I see the way you don't need much time to address my comments. So I'm super proud of that. The way this particular year, how you did all this work. And also, I want to say that I really enjoyed the journey, the learning process. And I miss seeing you in class. I miss seeing you like this experience that you see in this picture. Because a lot of times, as part of the green infrastructures, we walk out of the class and see green infrastructure, also discuss in person. Something that I do enjoy because I see you guys once. Seeing is different than just seeing the screen. Many of you, first time, to be honest, I met when you were presenting yesterday or on Tuesday. It was, a lot of you, I didn't even know you exist, in the sense I know your name, but I know who you are. So it was refreshing to see your face here. So if you are presenting today, when you present, obviously I don't impose on that, but if you keep your video on, that would be nice. And also, I want to say that some of you struggle, but it is part of learning. And I also see you grow during that struggles. You learn. So I'm very proud of you in that process. And you did very well in during the pandemics. We all struggles. I myself struggle during pandemic. You see that my son sometimes come running, and there are a lot of things we go through. And I understand that you have done so well despite all that we have lived through. So what I'm really proud of what you guys have done, and I love to see you guys, working in wherever you want. But if you want to know what we work on, because this class is very much our research, you can follow us on SEAL Lab website. This is the Instagram. You can see that's where we discuss about, not discuss, we share news related to lab, we share related to student achievements. We also share fun facts related to our research. So that's the Twitter and on Instagram handles. We have a Twitter account, but anything I submit on Instagram, it goes to the Twitter. So it's normally you get both. Also, our lab is on LinkedIn. That's the link over there. And also on the Facebook, there is a C Lab Facebook page. It's all linked there. So these are things you can know latest information about green infrastructures. If you are in this kind of business, or if you want to pursue this as a career, you might find those interesting. And finally, as I said, I I love to get connected with you throughout the life because LinkedIn gives us that access. So if you want to connect, this is my LinkedIn account. Feel free to reach out to me anytime you need any help. So I would say that's all I have in terms of how what I wanted to say. And this class has been, as I said, I'm pretty this year particularly, the projects are outstanding. And you all, it shows how the effort that you gave, because I saw the discussion, I saw there are stuff that I didn't think about. You guys all did it. So I always look forward to these presentations, and if we don't get to, we'll stay until everybody present. But I know that it may ended up becoming after 6 o'clock. If it does, I'll be present. I'll listen to every single presentation today, because that's the last day I could be here as part of the class. After that, tomorrow I can't see you guys. So thank you all. Let's have presentations today. And who are going to go first?
We'll go first.
You're going to go first, a compost group. All right. So I also want to say that I forgot what I want to say. All right. I think something related to projects. But anyway, I lost my chain of thought here. Okay. You guys go ahead and send me a link, or you have the link.
We sent you the link, but if you'd like, Emma can screen share too.
Yes. Go ahead and start the process. Again, it's a 12-minute. And for interest of time, we'll not have discussion during this like we did last time. You'll present. I'll just give very brief comments, 1 minute, then we move on to the next one.
Last time, Professor, you asked people to start by saying, oh, this is part of the green infrastructure class at UCLA. Do you want us to do that again?
That's okay, because this is part of the recording. I don't want to break into multiple ones. So this is going to be one recording.
Okay, thank you.
That'll save us time. And whoever not presenting, you can mute yourself. You guys do very well, but I am going to mute myself just in case, so that the recording quality is good. Okay, let's start with the compost group.
All right. Hello, everyone. So our project is entitled Start with Compost, and we took a look at how organic matter can be diverted to help support green infrastructure projects in Long Beach, California. Next slide.
Okay, so we started this project due to my work with a local food policy nonprofit, but Long Beach is a great study area in general because of our sensitivity to the climate crisis, the fact that we have existing policy in place, and the city also has pretty robust climate goals. So we're going to talk about implementing those policies into a circular economy to help improve sustainability in Long Beach. Next slide. So we made this graphic to kind of explain where our thought process was. So we're diverting municipal organic waste from Long Beach into sort of 3 segments. We're going to take the peak organic material and divert it into community compost projects that would stay within Long Beach. Tree trimmings and large wood matter would go into biochar production, and then everything that wasn't suitable for community compost would be diverted into an anaerobic digester. Now, what we would do is take all of the products from this and implement it into green infrastructure projects that are happening in Long Beach, specifically urban agriculture, the urban canopy, and stormwater systems for specific benefits. Next slide. So there was lots of benefits, but we're focusing on estimating the benefits of reduced greenhouse gas emissions, water treatment and conservation, and a reduction for the urban heat island effect. Next slide. And I'm going to introduce Emma and Ruby, who are going to take you through the stormwater analysis.
Okay, our first focus for our stormwater analysis was performing a literature review that looked into compost and biochar amendments in soil and how this could benefit stormwater treatment in general. Then for our actual analysis, we focused on an area in Long Beach that's near the Dominguez Wetlands Pump, which is shown on the bottom with all the flowers. We did this section because there's a Long Beach monitoring report, which gives the total pollutant loads and runoff values in this area, so it was a lot simpler for our analysis.
So our end goals, we're basically hoping to review research in compost and biochar-based stormwater contaminant conditions in Long Beach in hopes to provide guidance for suitable green infrastructures that incorporate diverted waste to treat stormwater in a more sustainable manner. And the Willow Springs Restoration Project is something that we hope to include as well. It provides a useful example of existing compatible green infrastructural elements and BMPs for urban stormwater treatment. And we're hoping to use these existing examples as a foundation for more compatible BMP types in Long Beach's region and its pollutant background.
Okay, and the main benefits that we found in our literature review for compost were increased plant nutrition, increase in unwanted substance removal, and then also it helps utilize food waste. The limitations that were found were leaching, and the use of immature compost can take away some of the benefits that you would get from a mature compost. For biochar, the main benefits were additional unwanted substance removal, increased microbial activity, and carbon sequestration, which helps combat climate change. It's also important to note that biochar's absorptive properties help combat leaching in compost by having nutrients released slower, so that we would be able to decrease the runoff from a first flush scenario through compost.
So some of the pollutants that we found from literature that are removed via biochar and compost combinations include phosphorus, nitrogen, polyaromatic hydrocarbons, microbes, dissolved metals, and oil, grease, even pesticides. And you can see an example on the bottom right of fecal coliform bacteria loadings that were reported from the Long Beach monitoring report. So what we also discovered was that across literature, phosphorus tends to have a lot of variability. For example, some compost helped, but other composts failed to make a difference in pollutant removal, and even some worsened nutrient leaching. But the key idea is that biochar has the potential to improve treatment in compost-based systems by absorbing water and nutrients and then slowly releasing that over time. And that's great for plant growth, and it also prevents the effects of the first flush pollutant discharge. And some of our other data came from the Long Beach monitoring report. You can see that in the middle. From this, we were able to gather a lot of data about the peak flow conditions, the stormwater volumes, rainfall, max intensity. And again, in the end, what we're doing is using all this data to summarize suitable combinations of biochar and compost ratios, as well as their types for use in Long Beach's existing stormwater and pollution background. And with that, I'll pass it on to the Urban Heat Island Effect group.
Thanks, Emma. Yeah, so for our section, you can go on to the next slide. We also structured it similarly to the stormwater treatment section, where we started with a lit review. And with that, we looked at different ways that urban greening can translate to benefits in terms of reduced urban heat island effect. And we incorporated in our research looking at how diverted organic matter could be incorporated into those urban greening projects to both enhance growth and, by extent, enhance mitigation of urban heat island effect. And from there, we took what we learned and applied it to a series of 3 geospatial analyses. The first was a NDVI analysis, which we used to look at greenness in Long Beach. From there, we generated some thermal maps to visualize urban heat island intensity across Long Beach. And then we wrapped it up with some reference maps that looked at other relevant information, such as various socioeconomic factors. Next slide, please.
Okay, so this map here on the right shows our NDVI analysis of the city of Long Beach. So what this NDVI analysis does is it shows the distribution of greenness. So as you can see, East Long Beach is much more green than West Long Beach. This is interesting because it shows there's not equal access to green space, but it's also interesting because West Long Beach is primarily where the industrial facilities and infrastructure that are more polluting are. So that is a health risk for the people who live in those areas without as much access to green space. Next slide.
So from there, we were able to download urban heat intensity data from a Google Earth Engine tool that had been created by a team at Yale. And the maps that we were able, or one of the maps that we were able to generate using that data is shown on the left side of the screen. And if you look at the zoomed in box in the lower left-hand corner, that shows the Long Beach area. And the important thing to note that kind of mirrors the map that we saw on the previous slide is that the west side of Long Beach generally has higher urban heat intensity values compared to the east side of Long Beach. And so that kind of mirrors how there's an increased amount of greenness on the east side. And this was seen across the maps that we generated for 4 years dating back to 2010. And so we used that data to generate the bar graph on the right showing that disparity in urban heat island intensity values. And this is just an important thing to keep in mind, both, you know, from an equity standpoint, but also to see that like if we increased greenness on the west side of Long Beach, there would be urban heat island benefits. And with that, we're going to pass it on to Ryan, Haley, and Tommy to talk about greenhouse gas emissions.
So we also wanted to quantify the amount of greenhouse gas emissions that would be saved by switching to this diverted waste model. And one of the ways that we would have mapped this was combining results of the UHI analysis that Madeline previously talked about, as well as a literature review. And with this literature review, we found estimates for an energy penalty in urban areas per unit area per UHI intensity. And this is what allowed us to quantify the cost to cool buildings in Long Beach as a result of the warmer city climate. And after finding these estimates, we found an annual average energy penalty, and averaging the cost of electricity in Long Beach over the period of a year, we found that the difference between East and West Long Beach was greater than $12 million annually. Next slide, please. So just to produce this amount of energy, there's going to be significant amounts of greenhouse gas emissions. And so using average values for emissions per kilowatt hour, we found that West Long Beach would emit 24 million kilograms of CO2 per year as compared to its rural counterpart. And for East Long Beach, we found that it would actually save 3 million kilograms of CO2 per year.
So another goal was to better understand the greenhouse gas emissions that come specifically from landfills and incinerators. And we included the incinerator data in our search because Long Beach operates one of the last 2 functioning incinerators in California. So from our literature review, we found that 1 million tons of food waste in a landfill emits about 1,100 metric tons of CO2 equivalent, whereas 1 million tons of food waste in an incinerator emits between 50 and 200,000 metric tons of CO2 equivalent. Next slide, please. So how will a diverted organic waste model combat these greenhouse gases? So for one thing, the breakdown of organic material under aerobic conditions, such as composting, contributes only minimally to short-term carbon cycle. And in the case of incinerators, diverting organic waste will make the heating element much more efficient, which will lower the amount of auxiliary fuel that is needed to run the incinerator. This will lead to lowered greenhouse gas emissions and can actually lead incinerators to act as a carbon sink when paired with waste to energy technologies. Next slide, please.
So the next 2 slides are going to go over 2 different intermediary calculations that were done to quantify waste diverted to compost to increase the urban canopy, which would decrease greenhouse gases and also the urban heat island effect. And so the first one shown here is a mass conversion between raw organic waste and mature compost. This is needed because basically during the composting process, mass is lost when microorganisms break down organic matter and they release CO2. So through literature review, we found a 31.5% mass loss from raw organic waste to mature compost. Next slide, please. And then the second one is basically finding the amount of compost per tree to increase the tree growth and increase the urban canopy. This was also done through literature review, and the different studies from the literature review were normalized using the nitrogen content of each compost in each study because nitrogen is the limiting nutrient for tree growth. And from these studies, we found a value of 49 kilograms of compost needed per tree. Next slide, please. Yeah, thank you guys for listening and being here for our presentation. We hope you enjoyed it. And if there are any questions, go for it.
We can clap virtually. I would say this was one of the most ambitious projects that I have ever taught. Okay, so it has so many components. Normally in any quarters, I usually limit them. I say that don't do that too many things. But I know Renette and all the teams were really passionate. So I say, okay, whatever you guys do, this your project. So I know that results is not going to be affected by that, by having this total, so many different analysis. I want you guys to challenge each other and that have the discussions, because that's more important than having, constrained projects. If so I saw that energy in your teams and I see that in your presentations. It's just there is just too much information and too much work you guys did. So great. I don't have any other comments, but if you guys have any other question, other students, they can ask. All right. So I think next group is, I see Green Beans group.
Yeah, I'll share the slides for that. Okay.
I like the first, that the picture holding the earth. Okay, go ahead. No distractions.
Good afternoon, everyone. My name is Amaya, and my group, the Green Beans, will be presenting our stormwater management plan for Pio Pico Middle School, which is located in Arlington Heights. So the motivation from our project comes from the effects of climate change and urbanization in the Los Angeles area, including urban heat island effects and water scarcity. Los Angeles hosts several contaminants such as heavy metals, which are picked up by storm. Communities of color and low-income communities experience disproportionate effects of these environmental hazards, which we took into account when we selected our site. So our objective is to use a combination of BMPs, including a green roof biofiltration system and permeable pavements to improve stormwater quality and reduce runoff.
So keeping an interest in implementing green infrastructure in Southern California, specifically LA, the location of our project is in Arlington Heights and intersects with the Baywinner Creek watershed, which is a highly developed watershed. The watershed has a dense population and overwhelming coverage of impervious surfaces that prevent runoff from infiltrating into the ground and contaminants such as trash, metal, bacteria, and pesticides. Then, to maximize the community benefits behind the Best Management Practice Project, the site will emphasize the implementation of green infrastructure at Pio Pico Middle School. Next slide, please. Justifying the positive impact green infrastructure can have on the chosen location, CountViro Screen 3.0 provides a demographic breakdown of a given census tract and scores the pollution burden found in the area. So from the test, the area scored high in people over the age of 25 with less than a high school education at the 82nd percentile, scored at the 89th percentile for population below twice the federal poverty level, 94th percentile for housing burden low-income households, 72nd for toxic release, and scored 4 out of 5 for the climate vulnerability index, to name a few parameters, which deems the area a disadvantaged community.
So to examine the flow, we took a cross-section using Google Earth Pro from the northwestern corner of the site to the southeastern corner. Our site is slightly lower at these two corners, and it peaks near the southeastern corner of the site. It results in an average slope of about 2%, and we expect the flow to go primarily toward that northwestern corner. Then I'll give it to Anna to introduce BMPs.
So our solution involves the implementation of 3 different BMPs: permeable pavements to help reduce runoff and remove pollutants, biofiltration, which filters contaminants via layers of filter media and vegetation, and a green roof, which can improve stormwater quality and reduce incoming peak flows.
The first BMP, which covers the largest surface area, will be a permeable pavement. The pervious pavement is the uppermost layer that will lie upon a base materials for proper drainage. Beneath that is an open crated crushed rock layer that will allow water to infiltrate away from the surface. We've decided to also include the filter fabric in our design to retain larger particles. As water slowly moves through the layers, the groundwater table can be refilled. And since the LA community is prone to flooding due to the high percentage of impervious surfaces, we wanted to minimize the possibility of flooding, worsening economic conditions in an already disadvantaged community. And while LA does not receive very high volumes of runoff currently, we expect climate change will bring about extreme periods of wet and dry. And to prepare for such events, we wanted to implement a BMP with a long lifespan and minimal maintenance. So we chose two different types of pavement based on function and appearance. Porous asphalt, which is seen on the right of the figure, is slightly coarser than concrete. And because its final appearance is a more attractive option, we thought it would be best to use for the highly visible parking lot and blacktops. This type is also just commonly used for larger areas and is easy to manufacture. Permeable concrete, which is seen in the middle, is lighter in color with a more reflective nature, which could be helpful during nighttime or early mornings. This type will replace the sidewalks on the school grounds, and car headlights can reveal if there are people or objects on sidewalks. This will also prevent puddles from forming, which could be a potential safety hazard for kids walking to school. This type is also less prone to cracking compared to conventional concrete options, which again can mitigate potential safety hazards.
And when determining whether permeable pavements were potential solutions for the issues impacting our sites, we looked at the following site-specific conditions. The area has a high percentage of impervious area with little room for infiltration, which leads to almost nearly all the rainfall becoming runoff. And as previously mentioned, the school is an economically disadvantaged area, so reducing runoff will reduce the risks of damages caused by flooding to the school and surrounded houses and families living nearby. Also, the area which we will convert to permeable pavements does not have heavy vehicle loads or high-speed traffic or high sediment concentrations that would normally damage the pavement, so it's a good site for permeable pavements. And then they can also act as a sink for pollution that would just normally run off impervious surfaces. And the installation would not be obstructive to just how the school functions, because it would just be replacing the current pavements and not just taking up any more space. And they will be strong for decades with minimal maintenance, like street sweeping and vacuuming, to ensure the pores don't get clogged. And once they do get clogged, you might have to replace sections of it.
Yeah, so the total cost of the installation of the permanent pavement includes materials, labor, equipment, and other general requirements, and it's just a little over $1 million. For all estimates, we assumed unionized labor rates, which is generally 20-25% more cost intensive than non-union labor. The unit of measurement is square footage. The unit cost is $675 per square foot. We also estimate the maintenance cost to be about $2,000 per year after installation in order to preserve the BMP and help maximize its life cycle. Then, yeah, I'll give it to Kathy to talk about biofiltration.
So the second BMP we recommended implementing at Pio Pico Middle School is a biofiltration system. As you can see here, this map shows the surrounding area of Pio Pico Middle School. Yellow represents, blue represents commercial, yellow represents commercial areas, and blue represents auto body repair shops. There's quite a few in this area, and pink represents residential areas. There are also several gas stations less than a mile away from the school, as seen here. These gas stations and auto body shops are potential sources of oil and heavy metal contamination in stormwater runoff. Additionally, the large residential area surrounding the school is a source of nutrient and pesticide contamination due to the many lawns that are in the residential area. Due to these pollutants from the surrounding area, we recommend a biofiltration system to be implemented on school grounds as a way to reduce the flow of runoff from exiting the site and would prevent pollutants from entering waterways like the LA River or the ocean. Additionally, with a biofiltration system, treated water can infiltrate the ground and recharge the groundwater table, which can help Los Angeles become a more water independent city.
So in designing the biofiltration system, we calculated the design volume to be 9,188 cubic feet of runoff for the 85th percentile storm event in LA. And this also takes into account the effects from both other BMPs that we'll be implementing, which are the permeable pavement and green roof. So this makes the biofiltration system the last point of treatment for runoff on the site. We then calculated the surface area needed to treat this design volume to be 4,324 square feet. And then as you can see in the picture there on the slide, we chose to place the system in the northwest corner of the school campus because with the elevation, this is the lowest corner of the campus, so all runoff will be sloping down towards this point. Next slide, please. And so the system will be 3 feet deep in total, just according to LA's design criteria. And so the layers in the system will include 3 inches of mulch on the top, filter media that's composed of 70% sand, 20% compost, and 10% biochar, coarse sand for the transition layer, and then gravel for the bottom drainage layer. We recommend this composition for the filter media because organic media such as compost that's augmented by biochar has shown better results in removing the pollutants that we're trying to address at this site. And then for the vegetation in the system, the vegetation must be suitable for the dry climate in LA. So we recommend using both the California meadow sedge and the clustered field sedge because both species are native to Southern California and they are both drought and flood resistant. Grasses are also more suitable for biofiltration systems in urban areas, and both systems are tolerant of foot traffic, which would be a benefit for a school campus where there might be heavy foot traffic.
The biofiltration estimate was similar to the permeable pavement. We had the same assumptions for unit labor costs and unit measurement. The only difference is the unit cost, which is about $9.80 per square foot, and it's a lot higher than the other costs because the bulk of the cost comes from the subterranean site work and earthwork.
Yeah, and now I'll talk a little bit about the green roof part of our plan. So our green roof is aiming to design and to add native vegetation to local areas, and it has an underlying objective to manage the stormwater. So we selected this system here because roofs have a lot of impervious land, as you can see on the left in green, and green roofs are effective at addressing that. It will simultaneously improve stormwater quality and reduce the incoming peak flows when the vegetation layer retains and filters a lot of that incoming stormwater. The stormwater will be captured from the available rooftop, and based on that, based on our design storm that Chella talked about, we can capture about 29,000 cubic feet that would otherwise become urban runoff. So the layers of our system are listed here in the figure on the bottom right. And notably, the growing material, the media, will be comprised of sand, mulch, and biochar, and we plan to make that about 4 inches deep. The filter will protect the drainage layer, and the drainage layer will temporarily retain some water in its depression cups, and any additional water will be removed through the drain. The insulation is an optional layer, but we recommend it because it can aid winter and summer costs for heating and cooling. We wanted to optimize the sustainability in our design, so we referenced strategies for low impact development in dense areas. So we picked drought tolerant plants, which is ideal for a dry Mediterranean climate because it will reduce the irrigation requirements. Weight is often a limiting factor for green roofs, so we minimized this by using dense and lightweight plastics, as well as a thin growth media layer. Walking paths will have to be placed around the green roof to prevent compaction and reduce maintenance needs, and fertilizers and irrigation will be needed as necessary.
And so the estimate for the green roof is a little different from the others. We broke it up into the insulation of the green roof itself and also the irrigation system. We thought it was important to break it up just because they have different associated maintenance costs. The irrigation system will require a lot more maintenance typically, even though in an ideal world, the system is installed flawlessly and lasts forever. Yeah, so I'll give it to Amaya to discuss challenges.
For the challenges associated with our plan, first, it'll cost upwards of $2 million to implement. So this is obviously a difficult project to implement on a small budget. The green roof does have the potential to save on energy costs due to its insulated properties, but it could take a significant amount of time to see these savings add up. Additionally, the site might need preparation before implementing the BMPs. For example, if the building for the green roof, if it doesn't support the weight load, then structural supports may need to be installed, which will have additional costs. And in particular, the cost to benefit ratio of the permeable pavement may not be as good because the primary benefit is infiltration of stormwater. And in Los Angeles, it doesn't rain too heavily, but Dawn did say that we do expect climate change to bring different weather patterns and for the permeable pavement to have a long life cycle with maintenance. And now for the benefits. Aside from improving the stormwater quality and reducing runoff, it provides many additional benefits. First, the bioinfiltration system or the biofiltration in the green roof system will promote biodiversity through implementing native plants. We're also introducing a lot of green spaces, and they can be used for activities like exercising, gardening, socializing, and this could improve the mental health of the students. This is particularly significant for our area because communities of color have historically worse mental health. And then the permeable pavement also has a cooling effect due to its evaporative cooling within the pores, which traditional concrete does not have. Next slide, please. And that's it for our presentation. So thank you so much for listening. Please let us know if you have any questions, comments, or concerns.
Thank you. I guess it took a little longer than I expected, but what you guys did is you present everything you wrote. You don't have to present in the normal cases. You can just tell the main stories, but everybody learned about it. Okay, I think we don't have much time for a break or anything, because I feel like we have still 4. Let's see how many groups more. Next is Civil Hall. Then we have we have also recording from 2 groups. So let's start with Civil Hawk. Or you guys want to take a 5-minute break? It's up to you guys. I hear a break or no break. If you let's say there are 2 signs here. One is clapping means break, and thumbs up means no break, or something like thumbs up, no break, clapping, break. I just see.
I think you can keep it going, Sanjay. In that way, because people are like watching, and if they need to drink water, they can.
Okay.
Presentations.
Okay. All right. Civil Hawks, the group. You're next. I like this sponsored pictures.
Okay.
Thank you, Professor. Hi, everyone. This is Xin, and we are Civil Hawk Group. Our topic is Spawn City. Let's get started. The rapid urbanization of our environment has resulted in increased urban flooding. It was caused by extensive use of concrete in urban development, resulting in an increase in impermeable surface. In addition, rainwater is discharged as wastewater rather than absorbed by the soil. Improper management of urban stormwater is not only harmful to human health, but also to authentic ecosystem. Therefore, new urban water management measures are essential for developed countries. The Spawn City project was launched in 2017 to 2014. It solves and overcomes the above problems by providing urban community with multiple benefits of reducing spills, improving water quality, improving water storage, and reducing greenhouse effects. But few Spawn City studies are based on a unified comprehensive study, mainly because the conditions in many politic cities are not similar. Another challenge is that most of the flow control of rainwater results come from simulation rather than actual measurements. So the goals of our project is to overcome the difficulty in data acquisition and review the achievements of Spawn City on runoff management, pollution removal, and elimination of heat island effects to give comprehensive planning options for Spawn City construction.
And then I'm going to talk about the approach of Spawn City design. The Sponge City programming is a strategy of the integrated urban water management that has been started in China. Sponge City refers to a city like a sponge has a good elasticity in adapting to the environmental change. When the rainwater resources are sufficient, we can observe the rainwater to decline in the peak flow. Also, the stored water can be reused as needed. The feature of the Sponge City should be friendly with the environment, combine the natural and artificial design, and emphasize the importance of the sustainable and low-impact development. The goal of SCP in China is more than 80% of urban land area will be able to reuse 70% of rainwater locally by 2030. About the construction of principle of SCP, we should protect the original urban ecosystem and emphasize the ecological restoration. And also, we should take the low-impact development to control the intensity of urban development. Next slide. The low-impact development is a site design strategy that uses infiltration and storage techniques to control the stormwater where it is generated. In this table, the first column shows the primary technical measures of LID, and we can check if the function of these measures is effective or not. And the economical cost, suspended solid removal, and the aesthetical value. The Sponge City programming will promote the use of LID to increase rainwater infiltration and storage.
Next, we will discuss about the function of a sponge city, including the stormwater management, pollutant control, and reducing urban heat island effect. This map shows the precipitation distribution for different cities in China. For the cities in red boxes, we will review the stormwater management performance. And for the cities in blue, we will review the performance of pollutant control. And finally, we will talk about the economic analysis for a pilot sponge city in Qingdao. The most common green infrastructure elements used in these studies are green roof, permeable pavements, vegetated soil, bioretention, and rain garden, as you can see in this picture on both sides. Next, please. First, Tianyu and I will talk about the stormwater management performance for these sponge cities in terms of runoff reduction and peak flow reduction.
In order to find the key factors deciding the performance of smart city rainfall control, we analyzed the data of 8 smart city programs, and we found that there is a correlation between green infrastructure L ratio and performance. This table lists four things: the 2 evaluation standards of stormwater management, which means changes in the runoff before and after the smart city construction. In addition, the average annual rainfall and the green infrastructure L ratio. The L ratio is adding up all areas of different types of green infrastructures and uses this value to divide the area of the project. The map shows the location of these 8 smart cities and their precipitation information. We can see most of the cities were located in rainy to semi-humid area, and most of them is located near coast. We use Excel to analyze data and plot 2 figures. This figure is about volume reduction. We can see a clear positive correlation between the green infrastructure L ratio and the volume reduction rate. By fitting a linear regression, this is the equation. And we can estimate for every 10% of green infrastructure implemented in the area, the runoff volume will decrease about 12.6%.
We also fit a linear regression for the total green infrastructure area ratio and the peak flow reduction. The positive correlation is found to be less than the one for runoff volume reduction. And from the linear regression equation we were getting, we can approximate that for every 10% of green infrastructure implemented in the area, there will be around 3% reduction in the peak flow. However, this could change as the soil gets saturated.
To investigate the pollutants removal efficiency of sponge city, we chose typical pollutants in rainfall runoff that affect the water quality. TSS, COD, TN, and TP as the relevant indicators in our study. Through case studies, we found that pollutant reduction ratios may be influenced by GI areas or rainfall events. So in this study, we were aimed at exploring correlations among them. We collected data from 7 cities. You can see in this map, these cities are located in humid or semi-humid region of China. Next slide, please. This figure shows pollutant reduction ratio versus GI area of 4 kinds of pollutants. A positive correlation between each pollutant and the GI area can be observed. For TSS and TP, the reduction ratio increases as GI area goes up. However, when the area becomes large enough, the pollutants reduction doesn't increase anymore, probably due to the limitation by other factors like rainfall intensity and duration. As for COD and TN, even with large areas, an increase in pollutants reduction can be observed, which suggests that removal of the 2 pollutants are influenced by GI area in a much more wider range. Next slide, please.
In this part, we want to know the relationship between the pollutant and the rainfall event. We found that sponge city is functional in decreasing each pollutant. We also found that the effect is obvious while the rainfall duration is short and the rainfall intensity is low. Next slide. Then we get 2 important results. If the sponge city area is big enough, the function of pollutant removal will not strengthen even if we increase more area. The sponge city may lose its function of pollutant removal when the rainfall intensity is too high or the rainfall duration is too long. Next slide.
Next slide. The urban heat island effect is a phenomenon whereby urbanized population centers experience warmer temperatures compared to their surrounding areas. The UHI effect is a culmination of factors, including the ratio of green space, sky view, building density, wall surface area, pavement area, albedo, and greenhouse gases, which all contribute to the entrapment and accumulation of heat within a city. Sponge city elements, such as urban greenbelts, parks, rivers, and water bodies, can be used to combat the UHI effect by reducing heat absorption and increasing evapotranspiration and shading. It was found that urban greening used in sponge cities could reduce air temperature as much as 4 minutes. Shading provided by trees reduced annual space cooling costs by 53 to 61%, and peak cooling loads by 32 to 49%. Therefore, through urban greening, it is possible to reduce energy consumption for cooling and alleviate the effects of climate change. Next slide, please.
So next up is a simple financial analysis of the city of Qingdao. The analysis was done following the PDF that was posted on CCLE titled The Value of Green Infrastructure, that included formulas to quantify certain benefits ranging from reduced runoff, energy use, and climate change effects. The total cost of development for this sponge city would be around $79,000 to $100,000, but the city would save about $1,000 a year from the avoided cost of water treatment, AC and heating costs of buildings, and the monetary value of carbon dioxide sequestered from the atmosphere. Next slide, please. Now that analysis was assuming a 50% retention rate of rainfall from each development, but the overall goal of a sponge city is to collect and reuse as much water as possible. So increasing that percentage to 70, 80, or even 100% would see a bit more savings per year. Also, if every building had a green roof installed, then the savings would double, assuming a 50% retention rate, or nearly triple with a 100% retention rate. But it is also important to note that it was difficult to put a dollar amount on benefits such as the quality of air, water, or even the quality of life of residents. And even though the savings seem very small, one of the biggest benefits would be the reduction of flooding that can cause hundreds of thousands of dollars in damage and even claim human lives. So the cost may seem high, but the benefits definitely seem to outweigh them. Next slide.
These are the conclusion of our main contents. Due to the time reason, I don't say that again. And that's all we want to show. And thanks for your listening. Welcome to any questions.
Thank you. I guess, this is the fifth time or fourth time somebody actually present on Spawn City. Every year, this is a hot topic. Anybody who, at least one group always chose Spawn City as one of the topic. One time, I think last year, there was one group who presented on, there was an explosion of chemical factory, and they says if you have a hypothetical Spawn City, how much pollutants would have been captured or treated right there. So this is this interesting site. All right, thank you so much. Let's go for the next one. Build. Who is the fourth one? The group, let's share your slides, then we can go for it.
All right. Hi, everyone. My name is Melanie, and today my group, Build Verde, will be talking about LA and how, more specifically, Southgate can incorporate green infrastructure in residential spaces to cool the city, preserve water, and improve community access to green spaces. In the next couple of slides, my peers will be talking more about what issues Southgate is currently facing. And in order to identify risks and prioritize the most concerning ones, we used NOAA's vulnerability framework, which the city of LA also uses. As the population of LA continues to expand, it is essential that they build sustainable structures to protect the community against climate hazards, as well as the infamous high smog level that LA has. All of these issues are resulted in the lack of green space for residents to enjoy. So our new housing unit that we're proposing in Southgate aims to alleviate the issues of air pollution, water scarcity, extreme heat, and in addition to that, provide a communal green space for its residents to enjoy. To accomplish this, we propose to implement vegetative green roofs, urban tree canopies, gray water reuse, and communal green spaces.
Okay, to provide some more background on the climate of our site, as indicated on the table on the right, Southgate has a relatively high heat vulnerability index, which means its residents generally lack the resources needed to manage extreme heat. And the graphs on the left qualitatively describe how extreme heat in areas like Los Angeles can be exacerbated by the urban heat island.
So in terms of air quality, this is a report from the South Coast Air Quality Management District in 2019 that just shows the concentrations of various air pollutants. And if we look at South Central LA, we can see that it has a higher mixed concentration per 1 hour of carbon monoxide and nitrogen dioxide compared to Central LA, but numbers for ozone, sulfur dioxide, and the other
Okay. Before we dive into our design solution, I will introduce what we want to achieve through this project. We hypothesize that as a result of our green infrastructures, the residents of our proposed housing complex will enjoy improved air quality and cooler temperatures during extreme heat events. And ultimately, we want to create shared green spaces that would increase community connectedness.
All right, yeah, so for the first green infrastructure that we intend on implementing, as said, is into the housing complex is the green roof. And so roofs are in general a strategic point to address urban cooling, as they make up upwards of 20% of an urban land cover, and this includes LA as well. And although they may require an additional irrigation demand, which might be a problem for dry land environments like LA, this can be minimized with the selection of drought-tolerant vegetation. And so green roofs and how they particularly improve indoor urban air temperatures is that they provide shading. They also increase the albedo or the reflectivity of the roof, thereby deflecting a lot more sunlight into the building. And they also cool the atmosphere with evapotranspiration. And so in semi-arid climates like Los Angeles, these are important processes during the summertime when the atmosphere is dry and extreme temperatures are common. All right, and so for specific design, we intend to use Sedum sediforme, which is a perennial plant that is drought tolerant and native to coastal Mediterranean regions. And one study has shown that it can last up to 88 days without irrigation, while also being effective at indoor cooling in semi-arid environments. And so for our design, this plant will cover the majority of the roofs, so approximately 1.8 of the 3.4 acres at our site. And of course, with the screen roof, there's other layers to it, one of which being the loam growth medium. This can be a 4-inch medium that will be implemented, and then some others as well. And then on top of that, we have barriers that are integrated into the design so that residents don't walk on the green roof elements, which would result in soil compaction. And in terms of maintenance, the roof is watered bi-weekly, cut back in the spring or early summer, and should be replaced after 45 years. Right, and so the cooling effects of this green roof can be estimated based on performance of green roofs using the same Sedum sediforme in other semi-arid climates. And so this table shows how that cooling has been seen in other Mediterranean regions. And so we can see that the reduction in temperature can range, indoor temperature can range between 1.87 degrees Celsius to 8 degrees Celsius. And so this is relative to a building with no green roof present.
So next we propose the use of urban tree canopies. Urban tree canopy can act as nature's air filter and air conditioning, so it can tackle both air quality and heat management, hence could also improve public health. It also aligns with LA's Green New Deal, which calls for increasing forest canopy, specifically in low-income heat zones, by 50% by 2028. For air quality, urban tree canopies can remove air pollutants and improve air quality in the area, especially since LA has one of the worst cases of air pollution in America. We proposed the use of street trees since particulate matter is the highest by the streets due to vehicular traffic emissions. Additionally, urban tree canopies can dilute and disperse air pollutants through barriers at the ground level using urban hedges, which can also reduce noise pollution, improve aesthetics, and provide privacy. As such, we proposed hedges to be installed around the perimeter of the housing complex, which would be especially beneficial for the apartments on the ground floor near the streets. As for heat management, the plants used in urban tree canopies can reduce heat through shading and evaporative cooling.
For our design implementation, we plan to put trees around the perimeter of the complex. And in our report, we outlined a few criteria for choosing tree species. And so those are picking deciduous trees as opposed to coniferous trees, taller trees as opposed to wider ones, low VOC emitting trees, non-flowering trees, trees that are suitable for sandy loam soil, which is commonly found in Southgate, and trees that are also resistant to heat, smog, and drought. And on the right side of the slide, we just also added a few examples of those trees. So for example, the London plane tree and the common hackberry. And next slide. So another part of our design implementation is hedges. And so urban hedges can improve ground level air quality for pedestrians and building residents by providing a physical barrier between the road and the sidewalk. And this increases the distance required for air pollution to travel from the road to the sidewalk, and that dilutes pollutant concentrations. And the figure on the left kind of demonstrates that. And in addition, if we use plant species that generally follow the criteria outlined in the previous slide, we can also increase the heat and air pollution related benefits. So On the right, I've just added a few suggestions for those plant species, including chokeberry, bayberry, and wild rose.
With an increasing population and not enough space, switching private gardens for public spaces has become essential. Communal green spaces allow for livability of the environment, but also provide outdoor excursion and experience of casual leisure for its residents. A study showed that the closer community is to a usable large green space, the more mental health disorders cases decreased within that community as well.
So one design we would want to implement in the future that would feel would be very beneficial to both the city of Southgate and those living in the apartment complex would be to include a system for gray water reuse. Gray water is used household water that comes from washing machines, bathroom sinks, and showers. We would not consider other household locations such as dishwashers, kitchen sinks, or toilets to be gray water, as they contain grease, bacteria, fecal matter, and food particles, which would require a different type of treatment and filtration that would not be feasible for this project. And because gray water still has the potential to harvest harmful bacteria and viruses, we must be careful as to where we would place and distribute this gray water. Gray water that is not treated can be harmful to the human skin if come into direct contact and has the potential to spread airborne viruses and uses such as sprinklers. So we would be careful to map out our plan. And our plan for this design would be to collect the gray water from the apartment complex and then filter it, and then distribute it to plants and trees in our buildings that would not be used for human consumption. All right, so some benefits to this design would be the reduction of water consumption for our location. Implementing a gray water reuse system can save homes up to 40,000 gallons of water a year, which in turn would reduce the water bill. Though the recycled water can be harmful to humans, it can actually provide nutrients that would allow plants to flourish. This would be beneficial to the site as we plan to have many green spaces, and as we mentioned, our green roof would require bi-weekly waterings that would be approximately 58.77 gallons per day. So this would be a great additional design for our site. Some limitations to this design are maintenance requirements. So we would need to replace or clean the filter at least once per week. And we would only be implementing outdoor use because of the possible health risks that could arise and it being more expensive as well.
Another future opportunity that we wanted to mention in our project would be green parking spaces. So in general, for the project, we want to encourage street parking to maximize the space we have available. But as per green parking space availability and resident requirement, parking spaces that use green facades using climbing plants and a wire trellis system would be a good option, since they don't require building a concrete wall and are completely green. Some benefits include no extra structural support, added privacy, and cooling and shade for vehicles. And the last benefit would be that it is inexpensive and easy to maintain.
So to conclude, through air pollution removal, shade, and evaporative cooling, we hope that the green infrastructures proposed can help improve air quality and manage hot temperatures for the residents in the city of Southgate, where high population density and urbanization result in high harmful emissions and enhanced urban heat island effect. This can improve the residents' quality of life as their health is improved and their comfort is enhanced. Additionally, gray water reuse can make living in Southgate City more sustainable and hopefully more affordable in the long run, improving the living situation of the underserved community in Southgate. As discussed earlier, future developments also include installing designated green parking based on space availability after construction of the housing unit. This brings us to the end of our presentation. Thank you for listening and feel free to ask any questions.
All right. Well, I want to just have one comment that for gray water, you can't inject on stormwater. There is a regulation for it. For injection, you got to disinfect. That means you have to install AV disinfections. that all the gray water has to pass through that. So there is a policy for California because the concern that you mentioned will have pathogens. But it's a future that you have to use gray water because nobody will pay for the clean waters, because every time you will have this drought, you'll have lots of stress on them. Okay, so that's good. So we have any other remaining for the live presentations? I don't see in the comments. Okay, so we have two more presentations, G.I. Joe Bruin, G.I. Joe Bruin, and Miles Avenue Elementary School. Who is going to go first? Which one I'm going to play right now? If I don't hear from anybody, I'll just play whichever the first one in my list right there. Maybe it's alphabetical order. Okay, I'll not waste time. Let's play one of them. Yeah, if I remember now what I was going to tell you. Please, if you have not filled the evaluations, do so. Every time it shows less than 50% evaluate the class, that's just a negative sign. Whatever you have comments, you should give. But do fill up that evaluations. You must have received it, and it should be, I think the deadline is on Saturday noon. So whatever you have to, we have only 1.5 days remaining. Okay, so I'm going to share the screen now. No, let's see, stop sharing. I have to share with the sound. Okay.
Hello, we are the G.I. Joe Bruins, and our project is about strategies to combat antibiotic-resistant genes, or ARGs, in stormwater. Our group consists of Albert, David, William, Karina, Shireen, myself, Charlotte, and Brian.
So let's start off with what exactly is antibiotic resistance. This is the process in which bacteria develop defense mechanisms against antibiotics. Well, how does this happen? This can happen through two methods, vertical and horizontal gene transfer. Vertical gene transfer involves genetic material being passed down from parent to child organism, whereas horizontal gene transfer involves the same material being transferred laterally from organism to organism. The second method is extremely dangerous, as bacteria can transfer these resistant genes to another, creating a domino effect once having been introduced to an environment. This can result in antibiotic resistance bacteria, or ARBs for short, preserving and growing their population more effectively than bacteria without ARGs. Antibiotic resistance can be promoted by the presence of antibiotic residues, which continues this positive feedback cycle. And so resistance levels in stormwater can be linked to several sources. For example, agricultural use of antibiotics in livestock and the application of manure can be linked to increased incidences of antibiotic-resistant bacteria. As a result, runoff from agricultural areas is a source for antibiotic resistance in surface waters. Similarly, antibiotics and metabolites excreted by humans eventually reach wastewater treatment plants. The antibiotics that are not eliminated throughout the treatment process can be reintroduced into the environment, with residual amounts reaching surface waters. With few mitigation efforts on the levels of resistance in the environment, antibiotic resistance is a threat to human health in modern medicine. As such, the removal of ARGs and ARBs in stormwater can help lower exposure to resistant pathogens and lower deaths caused by ARBs.
There are three main types of BMPs, or best management practices, to remove ARGs in stormwater. Number one being constructed wetlands, which have many advantages such as being cost effective, they have a high removal rate of ARGs, and it's not advanced or unknown technology, so it's easy to use and maintain. The cons are that its efficiency is dependent on the age of the wetland, seasonality, and plant presence, and there is also a large land requirement, making it unfavorable for urban areas. Biofilters are the next option, and their pros are that they suit urban landscapes. They're low cost depending on the geomedia used. They remove many different types of contaminants, and they are low maintenance, making them sustainable long term. Their cons are that biofilter utilizes biochar. biofilters utilizing biochar show decreased efficiency over time, and the durability of the biochar decreases in areas with freeze-thaw cycles. So that's not an issue for LA though specifically. There is also potential for heavy metal contamination in the effluent. Lastly, permeable pavement is also a good alternative to impervious surfaces, so good for urban areas. It removes many classes of pollutants, and it can reduce runoff and improve groundwater recharge, therefore reducing the amount of curbs and storm sewers necessary. The cons are that its maintenance is very difficult as clogging is common. It has a lower durability than traditional pavement and a complex installation as it is still new technology, so not many people are familiar with it and how to install it.
Research has shown that different BMPs can effectively remove ARGs and stormwater. So for constructed wetlands, it has a removal efficiency of 45 to 95%. For biofilters, 38 to 99.8%, and permeable pavement, 39 to 98.6%. So the biofilters show the higher removal efficiency and are therefore the most promising BMP for removing ARGs. And we also found that introducing geomedia to the biofilter systems can increase that removal efficiency even more.
The three types of geomedia that we looked into are iron-based amendment, biochar, and zeolite. To give a brief description of each of these types of media, here we have the iron-based amendments, such as zero-valent iron powder and iron oxides that are added to the filter media. This media is derived from waste materials such as iron fillings and water treatment residue. Iron fillings use adsorption, coagulation, and activation to remove pathogens. And then we have biochar, which is a charcoal-like substance derived from the pyrolysis of biomass waste. There's several types of biochar, including wood and grass biochar that have different characteristics. Additionally, the temperature at which biochar is pyrolyzed also alters its characteristics. And we looked into wood biochar in this project and considered a pyrolysis temperature of about 500 degrees Celsius. In terms of zeolite, this media is composed of different minerals. This media is microporous and has high cation exchange capabilities. Natural zeolite can be exchanged with other ions to alter its characteristics. And in this study, we considered copper exchange zeolite.
When it comes to ARG removal, all three geomedias proved to be quite effective, having removal efficiencies greater than 80%. It is because they are so effective that it is more important to evaluate these geomedias based on their material properties rather than their removal efficiency. For example, metal zeolite and iron filings contain heavy metals, so there runs the risk of heavy metal toxicity in the effluent. So despite both zeolite and iron filings being highly effective and durable antimicrobials, the lack of long-term research on metal-based geomedias and the potential health risk of metal elution makes biochar more favorable. However, one strong argument can be made that metal-based geomedias are more resistant to fluctuating weather conditions than biochar. But in the proposed LA area, that is not a concern. Warm temperatures and intermittent dry-wet periods are common in the LA area, so extreme weather conditions are not an issue. In fact, the consistent warm LA weather can actually increase the removal efficiency of biochar, making it an even more ideal candidate for our proposed site.
On the right photo here, you can see the site that we choose to do an analysis for. It is just one street, North Whitsett Street, and the land use classification is primarily single-family development. We chose this because it actually has a nice area on the left side of the sidewalk, and the right side it has a whole median for us to do the biofilters on. Some assumptions we made is you can see the watershed delineation represented by the red rectangle. The first assumption is that water does not enter from the north of the red rectangle. The second assumption is that water that falls on the houses is routed to the front of the houses in the street. And then the third assumption is that water drains down the left and right side of the streets respectively. On the left side of the left photo, you can see the BMP locations being highlighted in the cloud. You can see where we're going to put them on the sidewalk, and on the right, there's the median there. Something important to note is that water actually will drain down primarily on the left side of the street just due to the water being routed from the houses to the front. So you're going to need to implement some cross gutters to make sure that we can fully utilize the median space on the right. So we use the modified rational method for our hydraulic drainage analysis. So the inputs that we used for the design storm for the 85th percentile are 1.16 inches, and that was gotten from the LA Hydrology GIS website. We chose a 74% imperviousness, and using GIS, we measured the area to be 4.5 acres. The outputs can be seen in the bottom left there. And in the photos, you can see just zoomed in the biofilter areas that we're going to be using with actual dimensions. And in the bottom right, you could see some calculations that we found using the drainage analysis for how much area would actually be required for the biofilters. Here you can see a 3D AutoCAD representation of our model for what would be implemented on the left side of the sidewalk. It's important to note that a model is not shown here for the median, but this model works just fine. It can just be scaled widthwise and lengthwise to fit into the median, as the median design constraints are less limiting. The important things to note here is that the white translucent area shows the ponding depth. There will be vegetation on the top. The first layer will be the biochar and sand filter layer, which is where most of the ARG removal happens. Below that is the sand transition layer, and below that is the gravel drainage layer. It is also important to note that we needed to linearly scale up the dimensions used for biofilters in labs in order to meet the 85th percentile water quality design event with the limited surface area we had available for construction.
Based on the removal calculations for the site we selected, we extracted an annual storm volume of around 163,000 feet cubed and an 85th percentile design storm volume of around 13,000 feet cubed as shown previously. Using around a 10% error margin for the concentration values due to the sporadic nature of ARG concentration readings and also rounding, we resulted in a significant drop in ARG concentration by the time the effluent leaves the single cycle biofilter, with around 200,000 gene copies per feet cubed using iron filling, around 45,000 gene copies per feet cubed using the standard biochar, and around 8,000 gene copies per feet cubed using zeolite. We got identical results for both the annual and the 85th percentile design storm.
Overall, a sand-based biofilter can produce at least an 80% efficiency in removing ARGs from stormwater, but having different combinations of geomedia can further improve the efficiency. We ended up choosing biochar as a filling because it works great with LA's climate and that it doesn't pose any health concerns. We do recognize that many issues can exist, such as bacterial runoff from the compost, clogging of the biofiltration system, and chemical weathering of biochar. In conclusion, we weren't able to find a lot of large-scale implementations, but we took what's already been proven and verified in labs and designed our own biofilter off of it. Still, many issues can occur with this approach, and we think analyzing and quantifying those issues can be one of the future research directions.
ARG is one of the biggest issues in stormwater. So I'm glad that they did some data analysis and saw some results, what kind of amendments would work. So we have two more presentations. I just received one, but before that, I'll play Mile High Elementary Schools.
Hello, everybody. Welcome.
Hold on, I have to share the screen.
To our CEE159 final project presentation. Today, we're going to talk about the green redesign of Miles Avenue Elementary School in Huntington Park, California. This is our team.
As an introduction, we've aligned our design goals with the Los Angeles Green New Deal plan. Some of these include increasing renewable energy and water sustainability, which will be outlined in a later slide. The site we've selected is Miles Avenue Elementary, and our overall goal is to outfit this campus with green infrastructure. And here's a geographical reference for Miles Avenue. Its specific location is Huntington Park, Los Angeles, as previously mentioned. The physical site is approximately covered by 86% impervious surfaces. Additionally, the school is located in an area that has been identified as a disadvantaged community by Cal EPA, and these are some of the reasons we selected the site for green infrastructure outfitting.
So this was a site that we chose to outfit with green infrastructure. The total area sits at about 38,000 meters squared. As you can see, there's large unutilized spaces, there's a large blacktop area. About 15% of this area is covered with trees and 86% is covered with impervious surfaces, of which 31% is buildings, so that can't be changed. But the other 55% or so, we wanted to try to incorporate some green infrastructures. We were designing for the 85th percentile 24-hour storm intensity, and that's the number we used for our green infrastructure calculations.
In this project, we set out to accomplish three related goals. The first was create self-sufficient energy and water cycles, meaning we wanted to build green infrastructure that would capture enough energy and water to sustain the energy and water demands. The second goal was to promote sustainability, education, and health, which are achieved by the very presence of natural greenery and exposure to the green infrastructure. The third was a goal that would be related and resultant from the first two goals, which is reducing pollution and the urban heat island effect.
So this is the map of the site after our green infrastructure implementation. We cut the amount of impervious asphalt in half. We incorporated over 40 community garden plots and incorporated over 1,000 meters squared of bioswales and other native vegetation. We also rearranged the playground areas and incorporated over 4,250 meter cube of turf playing fields. And we also added solar panels to the roof to cut down on energy, but the rest of the team will expand on that later.
So now we're going to go through the energy cycle analysis. So Miles Avenue Elementary School has a total population of 980 students, which is a relatively high population. For this reason, we use the 95th percentile energy demand and to calculate the demand value of 13,728 kilowatt hours per year. We believe that solar panels is the solution to this dilemma. You can see here that we're going to install the solar panels on one of the roofs of one of the main buildings. So we believe that the system size that would be the best combination of energy capture and price would be 94.4 kilowatts. This system size would have an upfront cost of $283,000, which seems like a lot. However, the annual production from the system would be 155,000 kilowatt hours. And when you calculate the net annual revenue that the system would generate, it would be around $23,000. The payback period for the system would take around 12.5 years, which is about half of the system's lifespan. So that means the system would generate about $280,000 in revenue following the payback. Now we're going to go through the water cycle analysis. So Miles Avenue Elementary School has a water consumption of about 6,700 cubic meters per year. So we decided to implement green infrastructure to try to satisfy this demand.
Proposed green infrastructure is natural turf, and Bermuda grass is our selected grass species for this turf, as it is a native species to Los Angeles and is able to resist its dry climate, so it requires less irrigation than other grasses. It can serve as a field for athletic use and it has the ability to reduce the urban heat island effect.
So we propose the implementation of an extensive green roof on our site. It would sit on top of the existing parking structure, which is already used for recreation. For this reason, we believe it would be a good site for an athletic field. And we chose Bermuda grass as the vegetation that would be the best fit for the site. And we also chose 20 centimeters of soil for the growing medium, which would reduce irrigation demand. And then the rest of the layers of the green roof would be the standard layers. And this green roof would capture about 476 cubic meters of water per year.
So one of the biggest issues at Miles Avenue Elementary School is that it's covered by 86% impervious surface. most of which is blacktop in the parking lots and on the playground. This surface contributes to both increase in runoff and pollution of stormwater, as well as raising the temperature of the school grounds due to the urban heat island effect. To mitigate these issues, we decided to install permeable pavement in the school parking lot, on the playground, and on the running track, as it allows for water to infiltrate into the ground during rainfall events, which reduces surface runoff and has the potential to reduce the urban heat island effect through evaporative cooling. So since our project design requires a lot of water to maintain, we decided to include an underdrain with a raised outlet and an impermeable liner below the reservoir layer to maximize stormwater capture. So we use 3 different types of permeable surfaces. So for the main playground, we use pervious concrete. For the parking lot, we chose permeable interlocking concrete pavers. And for the running track, we used 100% recycled rubber. So the total volume of water captured by the permeable pavement system is estimated to be 1,391 meters cubed per year.
So with design goal 1 and 3 being stormwater capture and decreased urban heat island effect, we decided that it would be beneficial to install a biofiltration swale next to existing drainage and along the edge of the parking lot. So as you can see in this diagram, we have 2 impervious catchment areas that will remain impervious after all other green infrastructure installments. And we calculated the sizing for bioswale 1 and bioswale 2 based off of these catchment areas and the characteristics of the site. And then in this diagram on the left, I kind of illustrated what these swales will look like from the side. Obviously, they will both have different widths, but they'll follow the same formula for each of the components. So the swales will have rocks placed at the inlet for the pre-treatment phase to avoid flooding the bioswale and risking erosion or reduced infiltration. And then for the plants, we're going to plant native species that don't require as much water, but they can still ensure stormwater capture without needing to have a lot of maintenance. Then the retention area was calculated to be 1.5 feet deep for the ponding, just to maximize infiltration and groundwater discharge. And then for the filter media layer, we'll have a 3-inch layer of mulch on top of a mixture of sand, topsoil, and compost for the bioretention mix. And the recommended depth for that is about 3 feet. And then this transition layer will just be coarse sand. And that will just help further the infiltration and capture extra pollutants. And for the drainage layer, we will have a perforated pipe running through a layer of gravel. And then that treated water will be collected from the underdrain and sent to a catch basin for reuse. And so based off of our calculations, we estimated that the bioswale would capture 51.6 cubic meters of water per year. And not only will the bioswales help with stormwater capture and decreased urban heat island, it's also just generally an enhancement of the aesthetic values of the community. And it will just basically benefit this campus.
To collect the stormwater that will result from an increase of permeable surfaces, we would implement an underground cistern that will collect water from the green infrastructures. Before it reaches the cistern, it'll go through a hydrodynamic separator for filtering and then into the cistern. We'll then reroute this filtered water to the community garden to improve the school's water sustainability.
And here is our annual water cycle. Although we project that the water cycle will not be self-sufficient and design goal 1 will not be met, we believe that a lot of the costs that we incur in terms of water costs will be used to help us create a self-sufficient energy cycle, as well as meet our various other goals that we proposed previously. And now we'll talk about the social benefits. So for the social benefits, we propose to build a community garden using planter boxes to grow nutritional food crops, as well as native. Hello, everybody. Welcome to our CEE159 final.
For some reason, it restarted, but I guess see.
That was the project that
I showed in my presentation.
Yeah.
We're at the gardening
with the
section.
contrast.
No, let's see. This is where it get cut off.
Keep going back a little bit more.
This one.
No, one more.
This one, yeah.
Yeah.
Let's see.
It has been noted that the implementation of green infrastructure can have positive health and developmental effects on children in school. The addition of green infrastructure helps to increase the social capital of an area by increasing the space for the community to come together and interact with one another. In schools, it can also block out excess sounds and pollutants, which will help mitigate stress that students experience throughout the day, resulting in the students having a better environment to learn and engage with their schooling.
And finally, we'll be touching on the urban heat island effect. So to address this, we propose increasing tree canopy coverage at Miles Avenue. Trees can decrease surface and air temperatures through shade and evapotranspiration. Increased green space also has numerous health benefits, as Seth just mentioned, and they can also help decrease runoff volume by intercepting rainfall and increasing the lag time during a rainfall event.
To conclude, we have 4 main points that our project fixed. We wanted to reduce the water runoff at Miles Avenue Elementary, and especially do this while decreasing the peak rainfall intensity and untreated runoff that will be entering the sewage system and will remaining untreated on the surface in stagnant puddles. We also wanted to ensure that we'd be able to satisfy the energy demand of the school through solar installation, and we wanted to improve the social capital and learning environment for children in the area.
Thank you very much. Any questions?
Okay, this one is, I must say this is one of the cleanest slide I have seen. This was well made. They presented well, and they just keep the picture, so it helps me focus on the materials, because if I have slides both writing. So good job on that. So we have one more presentation, so even though it's going to be 5:50.
Also, I don't know if the group is here, but this project has a really good chance to be applied for the EPA Rainworks Challenge in
Yes,
September. So keep an eye out for that.
Yeah, so I guess, the way, I think there are many students who presented for the school as one of those their slides. So I think it's nice that we have so many real school applications. So let me close this one and share another one. Let me see if I can share. Yeah, this is okay. So the last one. Hold on, let me stop it, and I'm going to share the sounds. Okay, share the sound.
Hello, so today we will be presenting on a filtration park that we plan on implementing in Seattle's industrial district. The people that have worked on this project are Gap, Courtney, Annabelle, Simon, Katie, Jacob, George, and me, which is myself. And yeah, okay. So our area of study is the Duwamish Waterway located in Seattle, Washington. So as a result of the industrial district that's located near the waterway, chemicals such as arsenic, various polycyclic aromatic hydrocarbons and PCBs are found in the runoff, consequently being found in local fish tissue and the waterway. Moreover, this waterway is located near low income and communities of color, furthering the disproportionate effects of pollution. We plan on creating a filtration park to mitigate these effects of these contaminants and the runoff. Pictured here, we could see the outline of the waterway and the runoff area in relation to the park that we plan on implementing. Various health detriments are found from arsenic, PCBs, and PAHs which are found in the waterway, including the impact of young children's memory, attention, motor skills, and language development, and ultimately a risk of death. Fishing culture is also prominent in this area, and there is hence a higher risk of ingestion of this very highly contaminated fish. With the bioaccumulation of these contaminants in our shellfish, crustaceans, and fish,
The cycling of these contaminants in the ecosystem are detrimental to both ecosystem and the humans. Our green infrastructure plan focuses on addressing these ecosystem concerns by revitalizing river wildlife and protecting people from these contaminants.
So our project has three main objectives. The first is to reduce those toxins like arsenic, PCB, and PAH in the water, and subsequently in the wildlife. The second is to provide recreational opportunities. And the third is to educate and engage the community with green infrastructure and to connect that to the resulting health and environmental benefits. So specifically for our green infrastructure, we plan to implement multiple methods for toxin removal. These include a sand filter with added amendments as a primary treatment. And then between the sand filter and the river, we will implement a wetland designed to remove both arsenic, PCB, and PAH via adsorption, precipitation, and phytoremediation.
Here's the layout for our filtration park in the industrial zone of Seattle. Runoff from the industrial district containing arsenic, PAHs, and PCBs prior to entering the Duwamish River will be treated by 3 layers of our GI system. First, it will encounter rocks and prairie plants such as blue wild-rye Canada goldenrod, which are represented by the blue stars, to slow flow and phytoremediate some pollutants. It will then enter a sand filter, which will include amendments to help biodegrade our targeted toxins. And lastly, it will enter our wetland, which will include a mixture of native plants that degrade pollutants. And so the stars in this diagram represent different plant species with a table on the side to further elaborate. We have plans to enhance conditions for degradation in the rhizosphere and microbially inside the wetland in red and purple colors, such as duckweed, rush, reed, and grasses. And we also include hyperaccumulating willows along the border to shown in yellow and green, to prevent pollutants from entering the Duwamish River. Lastly, our GI system will include a walking bridge with multiple entry points running parallel to the Duwamish River for community members and visitors to enjoy in the Seattle area to add recreational value to our system.
Okay, so from the research we did, iron oxide seems to be the best amendment for removing arsenic. Many countries in Asia actually use iron oxide as a filtration system for arsenic. Arsenic has a -3 charge, while iron oxide has a +3 charge, thus they attract each other. As you can see on the figure to the left, iron oxide by itself can absorb all of arsenic in a lab setting. The figure on the right shows how effective sand mixed with iron oxide is. It shows that 5 grams of sand amendment with iron oxide should be added for every 100 milliliters of arsenic. This is the most effective and can remove up to 97.5% of arsenic.
We also researched sand amendments that could remove PCBs and PAHs and mainly found that studies on activated carbon and biochar. There is significantly more research available on activated carbon, which showed a high removal capacity of 70 to 99% for both PCBs and PAHs in lab settings. And while activated carbon appears to be very effective, it is also expensive, which is why there is some research being done on biochars for organic contaminant removal. Most types of biochars show a slightly lower absorption and removal capacity than activated carbon, around 50 to 80%. However, chemically activated biochar did show a competitive removal capacity. Biochar is much less expensive than activated carbon, so this is a promising area for contaminant removal that needs more research. The picture we have here is of a biochar made from peanut shells, which shows almost 80% reduction of PCB concentration in one study.
For arsenic removal through absorption and precipitation in wetlands, we plan to use a gravel with a high iron content as the bedding, as gravel itself does not absorb arsenic well, but iron does. We also plan to introduce sulfate-reducing bacteria, or SRBs, to aid in arsenosulfide production, including species of Desulfovibrio sulfodismutans, Desulfobacter hydrogenophilus, as these species precipitate insoluble species of arsenic that are less toxic than their ionic forms. We also plan to include mineral amendments with a high arsenic removal capacity of more than 99%, including limestone, zeolite, and ferric oxyhydroxides. However, there are certain environmental conditions necessary for these absorption and precipitation reactions, including a pH of slightly basic to neutral for absorption and anoxic conditions for our SRBs in the subsurface environment. Therefore, we would need continual monitoring of the wetlands to ensure these conditions are met. For the inclusion of plants in wetlands for arsenic removal, arsenic is released upon decomposition of plants, hence the need for harvesting. However, there are root soil interfaces responsible for arsenic absorption, precipitation, and chelation through microorganism interactions that create optimal oxidative and reductive conditions. The inclusion of insoluble organic matter such as humic acid is beneficial for arsenic absorption as the insoluble organic compound has a high absorptive capacity for arsenic removal. And finally, some example species to include in our native wetlands for arsenic removal are Salix lysandria, Pacific willow, Lemna gibba, which is duckweed, and Spirodella polyrhiza, which is great duckweed.
So for our PAH and PCB organic contaminants, we will also be implementing some plants for phytoremediation. So these could include common rush, small fruited bulrush, and woolgrass. And because these are organic contaminants, the plants can actually break them down fully. And so there's no need to harvest these plants.
So now we'll move on to how our research applies to addressing our objectives. Our first objective was to reduce the amount of arsenic, PCBs, and PAHs flowing into the water and bioaccumulating in the aquatic life of the Duwamish waterway. After our research, we decided to choose iron oxide coated sand and activated carbon as amendments for the sand filter park, since they showed high removal capacity for arsenic and PCBs and PAHs. We estimate that the sand filter portion will remove a majority of the targeted pollutants from the runoff, and the rest of the pollutants will be removed by absorption and precipitation in the wetlands. We were able to find many plants native to Seattle that are hyperaccumulators for our targeted pollutants. So by the time the runoff has passed through the wetlands and reaches the Duwamish waterway, we believe that it will have negligible concentrations of arsenic, PCBs, and PAHs. And this will help the waterway meet its TMDLs for those pollutants. Additionally, reducing the pollutant concentration in the waterways will help to reduce the bioaccumulation of those chemicals in the local aquatic life.
Our second objective was to provide safe recreational opportunities near the site with functional remediative benefits. Our green infrastructure plan not only functions to reduce toxicity within the Duwamish waterway, but would, as a result, help improve the surrounding ecosystem and wildlife. A study done in the Duwamish industrial area found that salmon died within 4 to 6 hours when exposed to stormwater runoff from a local highway. However, when researchers filtered the highway runoff through a soil mixture first, the salmon had a 100% survival rate. Therefore, by targeting the region's area of contamination with our green infrastructure plan, we can not only improve ecosystems within the industrial regions, but also improve the habitat throughout the Green Duwamish River and initiate necessary salmon remediation. Our final objective of this project was to educate and engage the public on the use and benefits of green infrastructure for a safer, more sustainable future. Our infrastructure plan could allow for more sampling as both a learning tool for local educational groups and a means for predicting rising air pollution levels. Utilizing the plants in our wetlands to track air quality could potentially prevent future air quality crises in the surrounding Duwamish River area. Additionally, access to the wetlands provided through the designated boardwalk would enable a safe and educational space to bring students and city residents on educational tours through the established infrastructure, during which they could get hands-on experience sampling moss for air quality, as well as learn about the sustainable design of the park.
As we conducted our research, we learned about the environmental implications that these solutions would cause. We concluded that the ideal remediation techniques to use for our site on the Duwamish waterway was using iron oxide amended sand filters, which we talked about previously, activated carbon amendments as well in the sand filters, and a mixture of native plants that hyperaccumulated pollutants like arsenic and other organic pollutants. And while we learned a lot through our research, we did have a couple of research questions that we'd like to pursue after this. One of which was wondering if we could implement biochars in our wetlands as well as our sand filters. And we also wanted to learn a bit more about the optimal harvest intervals to prevent re-release of contaminants like arsenic into the waterways if the plants that absorbed them died and were releasing those pollutants back into the environment. And thank you for listening. That's the end of our presentation, and we'll open it up for questions and we can hopefully give you some answers. Thank you.
All right, so I guess one comment is that you can mix iron chloride with biochars and or pyrolyzed biochar, so that will create more iron in it. So you don't have to have two different things at the same time. So that's really, I just want to say that the way I evaluate the presentation is based on story. I don't take any points. I didn't say that before, but obviously if there was really bad presentation, I take some point up. All of you get 10s on that, 100% as far as presentation is concerned. So great job, you all. I am going to read the presentation, not the presentation. I'll read the your projects and send you comments. So keep an eye on it. As soon as I send you, within few hours, you can edit everything and send me back. I'll upload the grade because all the things are memory in my, know what I commented. So fantastic. So what I'm going to do is, I know that 39 of you are here. I don't think next year will be on in person for sure. By this year, this is a unique experience for us. Any of you, I'm going to take a screenshot, but many of you are just at the nobody's saying the first. So let's do it for one time. Let me make the screenshot. So I'm going to share with the campusware. Okay, so I'll take one screenshot. Let's see. So we can make all sorts of face, happy relief face that finally is over, whatever face you can. Tida, you have your mask, so you I know you are in the lab, so that's why I understand. So that shows that you are working in the lab. Okay, I'm going to take one shot. Okay, 1, 2, 3. I'm going to take another one because in my screen there are like two spots. So let me save this one first. Okay, let's see. Hold on. I want to make sure that I don't lose it. It's a big file. Okay, so let's see. I'm going to take another one, the next screen. Screenshot. Okay, thank you. All right, so that's at least I got it. So I'm going to post that on the campusware. So you guys, if you want to.
Looking good, Rain.
Yeah, well, thank you so much. I good luck if you guys are graduating. I'll hope to see you, meet you sometime. But if you are still here, maybe some of you I may not recognize you if you don't ever come on online. So don't feel bad if I don't recognize you because I didn't meet you. Remind me. And also, obviously, if you need letters of recommendations, because this is where I write projects with you, it is a lot easier for me to write letters for you because I can highlight those writings as well as presentations. I can talk about team, so many things I have, obviously. Again, don't hesitate to reach out to me. And remind me if I don't respond email, doesn't mean that I don't want to respond. I may missed it. So it's your rights to email me as many times you want to. Okay, I don't mind for that reminders. Again, good luck with your finals for other classes. I know this is not the final. As far as your projects, I have at least seen it, and thanks to Renan, you guys has improved a lot. So I don't have much comments in many of the projects. So I'll give you those comments, and good luck with submitting the final report. All right, so 606, that's the longest one, 2 hours presentations. Thank you again.
Thank you, Professor.
Thank you,
Thank
Professor.
you.
Thank you.
Thank you, Professor.
Thank you.
Thank you, Professor.
So Ambrose, you are graduating?
Thank you so much. Yeah, I am graduating.
Are you going to UK or where you're going now?
Well, I'm still in Hong Kong. I feel like I might just like take a break and
Okay.
then start applying for jobs first, and then I'll probably apply to grad school like next year.